Welcome to the first video on scalar product or dot products of vectors. Some of the prior knowledge for this video include vector operation and geometric operations, and it will be useful if you have watched the force and displacement videos. Let's start with a real-life application of dot products. We have a box here, and this person is going to be pulling it with a force, which is 30 degrees relative to the ground, and this person is going to displace it with vector delta d. The definition of work done using a force is the product of force and displacement, but they need to be in the same direction. So they either need to be in the direction of displacement or the force. So this means that if we have the two vectors, the force and the displacement, separated by angle theta, we can take the component of force that is in the same direction of displacement. So the force is the hypotenuse, and we got the angle theta, and that side, which is in the same direction as the displacement, is the adjacent to the angle. So that's force times cosine of theta. And now, based on the definition, we can come up with an equation. W, which is work, it's measured in units of joules, is equal to the displacement, which is often measured in units of meter, multiplied by the force in the same direction, which is the magnitude of the force multiplied by cosine of theta, and force is often measured in units of Newton. Now, we can rearrange this and write it as W is equal to magnitude of force times magnitude of displacement times cosine of theta. And another way of writing this, because it's used so often and something that we'll come back to, is we can write it as vector F dot vector delta D. And this is what we call the dot product. And our final answer, whatever we get out of this, is actually a scalar quantity. So by definition, scalar or dot product of vectors u and v is equal to the magnitude of u times magnitude of v times the cosine of the angle between them, and that angle between them is always between 0 and 180 degrees. When we have vectors, we often are given those vectors in their x and y components, or x, y, z components in 3 dimensions. So we want to figure out how we can use this information for the dot product. So we have two vectors, u and vector v. So we're going to draw them out. Vector u and v in space, they're attached to each other. And I forgot to put the arrow on the u here. I do apologize for that. And now vector u minus vector v would mean that we're subtracting all the components of x and y of vector u by vector v. To do this geometrically, what we're going to do is we're going to take vector v, take its opposite, and add it to vector u. And the resultant vector is the same vector that is starting from the head of vector v and going to the head of vector u. And they have the same magnitude and the same direction. Now we have formed a triangle. It has 3 sides, one that has magnitude of u, one that has magnitude of v, one that has magnitude of u minus v, and the angle between u and v is going to be angle theta. Now we're going to use the cosine rule, and using the cosine rule we can see that the magnitude of u minus v squared is equal to the magnitude of u squared plus magnitude of v squared minus 2 times magnitude of u times magnitude of v times cosine of theta. We're going to use the idea that the magnitude of a vector is its x component squared plus y component squared, and we're going to plug that in for u minus v, for vector u, and for vector v, and write the equation in this new format. Now we need to simplify this so we know that when a root is squared, it cancels that operation. So we end up getting ux minus vx squared plus vy minus vy squared is equal to ux squared plus uy squared plus vx squared plus vy squared minus 2uv cos theta. We're going to expand this to see if we can even simplify it further. So we expand the first 2 brackets, and we're going to leave the right side of the equation as is. Now the magic happens. We can see that a lot of the terms are shared between the left hand side and the right hand side, so we can subtract them from both hand sides, and we will cancel them out, and we'll end up simplifying the equation significantly, getting negative ux vx minus negative 2uy vy is equal to negative uv cos theta. We can do a little bit more simplification by recognizing that the negative 2 can be factored, and when we factor the left-hand side, we can see that we can divide both sides by negative 2 now, and once we do that, those values cancel out, and we're left with ux vx plus uy vy is equal to the magnitude of u times magnitude of v times cosine of theta. This looks very familiar. Magnitude of u times magnitude of v times cosine of theta is vector u dot vector v. So we now see that for a two-dimensional case, vector u dot vector v is equal to ux vx, which is their x components multiplied by each other, plus uy vy, which is their y components multiplied by each other. In this particular case, we proved this for a two-dimensional case. We could have done the exact same thing for 3 dimensions. However, it would just be a lot more values and more time consuming. And since the proof can be explained using 2 dimensions, that's what we did in this case. If you did have a 3-dimensional vectors, you can use the exact same procedure. So vector u, when it has components x, y, z, and when vector v has components x, y, z, vector u dot vector v is equal to the magnitude of u times magnitude of v multiplied by cosine of theta, which is the angle between them, and that's also equal to their x components multiplied by each other plus the y components of the vectors multiplied by each other plus the z components of the vectors multiplied by each other. When vectors are given in their component forms, dot products are extremely useful because they can be used to find the angle between the two vectors, and we'll show you that using an example a little bit later. Now, if two vectors are perpendicular to each other, it means the angle between them is 90 degrees. Since the dot products of two vectors is equal to the magnitude of one multiplied the magnitude of the other multiplied by cosine of 90, and since cosine of 90 always equals to 0, that means the dot product of two vectors that are perpendicular also always equal to 0. The summary of the concepts of this video is summarized here. If you want to pause the video and write them down, please do so. And now we're going to look at a few examples. For the first example, we want to calculate the work done by Robo carrying a box 200 meters and with a force of 40 Newton, which is 30 degrees relative to the force. We often start these questions with drawing the diagram. So in this case, we have the displacement, which is 200 meters, and we have a force which is equal to 40 newtons, and the angle between is 30 degrees. We know the work is equal to vector F dot vector delta D, and that's same as the magnitude of F times magnitude of delta D times cosine of theta. We put all the values in, 40 times 200 times cosine of 30, and we will get an exact value of 400 root 3 or an approximate value of 6,930 joules for our final answer. For the second question, we got Robo who exerts force F1 on a box and moves it for a displacement of delta D. We want to determine the work done and the angle between the force and the displacement, and we're given all the components of the force and the displacement. Whenever we have the components of two vectors, we can find their dot product, and the dot product of force and displacement is equal to the work done. So in this case, for the work, we're going to multiply the x components of the two vectors and add them to the y components multiplied by each other, and add them to the z components multiplied by each other, giving us the work value of 800 joules. Now, we also know that the work equation is equal to the magnitude of the force multiplied by the magnitude of displacement times cosine of theta, and that's the dot product, and that's also equal to 800 joules, what we just found. So we can find the magnitude of force, and that's its x component squared plus y component squared plus z component squared, and we'll get root 1400, or simplify to 10 root 14, and we can find the magnitude of the displacement. I do apologize, I did forget the magnitude sign. And once we do that, we get root 1100 or 10 root 11. Now we go back to our equation and we're going to rearrange for cosine of theta. So that's going to equal to 800, and we're going to divide both sides by magnitude of force and magnitude of displacement. So that's root 1400 and root 1100. And when we take the inverse cosine of that value, we get our angle theta is equal to approximately 49.9 degrees. For the final question, we are going to determine the value of x if vectors u and v are perpendicular, and vector u is given with x component of x, y component of 3, and vector v has components 4 and -1. We know when two vectors are perpendicular that their dot product is equal to 0, so we're going to multiply their x components together and add them to the multiplication of the y components, set that equal to 0. We get 4x minus 3 is equal to 0, and that means 4x is equal to 3. Adding 3 to both sides, divide both sides by 4, and we get the x value is equal to 3 over 4. I have prepared 3 questions for you folks to try out, and I will try my best to post the full solutions to these in a separate video as soon as I can. I hope that this video was helpful in giving you an understanding of the introduction to dot product and how they work. How is their algebraic equation related to their geometric equation? And the next dot product video will focus on their operations. Thank you for watching.